recording. So there we go. Welcome back, everybody. Happy Thursday to you. A relative heat wave, I think, relative to the past couple days. I'm told the weekend is going to be terrible. So, huzzah. But I know what you can do to keep yourself occupied during the weekend. You could start your first homework for this class. See, my homeworks are an excellent way to procrastinate on other things that you need to do and yet still feel productive. Because there are these nice, well defined tasks with clear answers. It feels good when you get it finished. So I would recommend that as a way to pass the time. I went ahead and put that up, I think yesterday. So homework one is available to you, although it is not due for quite a while. March 1st is actually when it's due. I thought it was going to be sooner than that, but then I realized I had pushed everything as far into the semester as I could, just in case we had issues getting started with things as we did last semester. So that is available to you whenever you want to work on it. First formative assessment is due on Monday, so if you could please get that done by Monday night, I can look over your answers and we can talk about it on Tuesday. So those are the updates to the schedule. I have posted new materials for today. So there's lecture 2, and there's also a separate document that is called example 2. So the previous unit that we just finished, lecture 1, is the only time that I'm going to have SAS and Stata code embedded inside the PowerPoint slides and then separate videos using the software. From this point forward, what I'm going to have are PDF handouts, uh, examples that go with each lecture that have the syntax and the output annotated all in one place so that we can talk about it as a whole. I do still have the raw materials though that I built the handout using. So right here, there's a link to example 2 data files. Those are the data set in Excel format, syntax and output both in Stata and SAS that built the handout. So all of the original material is there. That way, when you start homework 2, you can go straight here and copy the syntax and use that as a template to help you complete the homework. So that'll be a little more efficient than typing things in from scratch or trying to copy out of the PDF handout. So lecture 2 and then example 2. Probably won't get to example 2 today, but we will start with lecture 2 first thing. So any questions or comments before we dive into some stuff? No? We're ready to go? All right, then no place to start but the beginning. So this is lecture 2, Bivariate Association. So first, just a quick review. Where we've been thus far is focusing on univariate statistics. So terminology, univariate meaning one variable at a time, and statistic meaning something that we calculate using a sample, but usually we hope to try and make some sort of inference about our sample relative to a population. And the types of variables that we have discussed come in two main flavors. There's categorical and there's quantitative. So categorical is when the data may be stored as numbers, but they're not really numbers. They're kinds. So you may have binary, which is two kinds, ordinal, which is three or more ordered kinds, or nominal, which is three or more unordered kinds. And in order to describe any categorical variable univariately all by itself, all you really need to know is the frequency of each of the responses. From that, you can calculate the percentage. The percentage in each category would be analogous to a mean. There is really no such thing as variance and skewness that you would have to worry about because they're determined by the mean. So just knowing the frequency of each category is sufficient. You can throw those into a bar graph or a frequency graph to display that, and that's all you need to do. For quantitative variables, that's where the numbers are the numbers, so they may or may not have boundaries. For instance, if you have a count variable, that can't go below 0, so there's a lower boundary on that. If you have a variable that's a binomial variable, like a percentage, it can't go below 0 and it can't go above 100 or 1, depending on how you've scaled it, but you can have continuous variation in the middle. And for those sorts of variables, you tend to want to focus on three salient features. Central tendency, which is mean usually, sometimes median or mode. Now let me ask you, what's the difference between a median and a mean?
The mean is the average, and then the median is just the middle number, but within your set of numbers there.
Mm-hmm. Synonym for the median, by the way, cough, cough, homework question, is the 50th percentile. So it's literally in the middle of the data if you were to order it. In what circumstance would you expect the mean and the median to not give you the same answer?
When there is skewness.
Yeah, when there's skewness. So skewness means there's a tail to a distribution. If it's positive skewness, then the tail is heading in the positive direction. So for instance, a count variable frequently has positive skewness because it can't go below 0, but it can go all the way up to positive infinity. In that case, the mean is going to be pulled towards the tail, whereas the median will be less so. And so that's why for skewed outcomes, you tend to see median reported in addition to or perhaps instead of the mean. So let's see. We don't do much with mode, actually. That's really not a thing that people use, and there's not really statistical models that are built to try and recreate modes, although they are used in estimating models quite frequently. Other thing we want to check for, or pay attention to, I should say, is dispersion or spread. So that would be given by standard deviation and its cousin variance. How are those two things related? Do you remember?
Is it the higher the standard deviation, the greater variance?
That is true, although there's a more specific mathematical relationship between those two numbers. One is the square root of the other.
Yeah. Standard deviation is the square root of the variance.
Yes, standard deviation is this, and I said root, didn't I? Yeah, I need to have a little more caffeine, apparently. I slipped up. Standard deviation is the square root of variance. And so in practice, you only need one or the other to convey that same idea. Standard deviation is a little more useful because it's in the metric of the original variable. So the definition of standard deviation is that it's how far off, on average, any one case is from the sample mean. So that's easier to think about than squared offnesses. That's variance. That will become more important in thinking about the utility of a model in predicting a variable. We talk about its leftover variance as opposed to its leftover standard deviation. So that's coming later on. And then skewness, asymmetry, we've talked about, is the other thing you'd want to pay attention to. And typically to show a distribution of a quantitative variable, you do some sort of histogram, potentially a box plot, or there are more modern alternatives, violin plots, to make those sorts of visuals. And so that type of information would typically go in your methods section. You may have a table of results that would summarize frequencies for categorical variables, means, standard deviation, mean, minimum, maximum for quantitative variables, and other things as needed. So any thoughts, questions on that? Good? All right. So in terms of the scale of variables, that's one thing that I want to talk about quickly before we talk about bivariate associations, because scaling is going to be something that happens during the process of creating association statistics. That's sort of a mouthful. Let me back up and just I'll go over this slide here. So quantitative variables in particular sometimes have direct inherent meaning, but not often in the social sciences. So in the hard sciences, so to speak, and in certain applications, you may have real units of a quantitative variable like pounds, inches, dollars, things that you can sort of picture like what 1 is versus what 3 is. Frequencies and things that happen, number of hurricanes this year, number of cigarettes smoked, things like that. Those numbers have inherent meaning, and so you can work with those types of values directly, and people will know what you're talking about. That is not often the case for variables in the social sciences, in particular, variables that are created as sums of other items. So you may have a survey that has, say, 10 different items on it designed to measure one's tendency towards depression, something like that. And each item might be measured on, say, a 5-point scale for how frequently does this happen to you, going from something like rarely up to almost always. So in that case, you may not know what the number means that comes out of that. Like if I said, oh, I got a 31 on this depression screener, it's like, okay, is that good? Is that a lot? I'd have to know how many items went into it if it's a sum, assuming that that's what it would be in each case, as well as the potential range. So if each item is scored from 1 to 5 and I have 10 items, then that's somewhere between 10 and 50, right? So then a score of 31 would be somewhere in the middle, which would correspond to like an answer of about 3 out of 5 on average. So there's a lot of like back translation that has to happen to put some sort of more meaningful idea onto the number that's being provided. For instance, vocabulary tests, like if I got a 47, well, how many total were there? How many did you get correct? So those sorts of numbers you have to sort of push further. And because of that, these sorts of arbitrary metrics are often transformed to increase their interpretability. So ready alternatives to this that you may have already seen. When you have a number correct on a test, that's often reported as a percentage because people know what 80% means. They don't necessarily know what a 47 is. If you have, say, 10 items, for instance, for this depression screener, it's usually more interpretable to think about the mean across items rather than the sum, because then you're on the scale of the original item response categories. So if 1 means this, 2 means this, 3 means this, adding them, of course, pretends that they're interval rather than ordinal, but that happens all the time. A mean of 3.1 would mean that you're somewhere around whatever 3 indicates on average, which is then a little more directly interpretable than whatever a sum would be. Another example of this, the GRE. Most of you probably had to take the GRE to get here, myself included. Boo, or didn't have to. Boo, is this what we missed today?
Like, did not like it. It sucked.
Boo, the correct answer is boo. Yes. Yes. When I took the GRE, I was one of the first people to take the newly computerized adaptive version, where it was adaptive by item. So are you familiar with the idea of computer adaptive tests as a concept? Yeah, they only administer items that are supposed to be relatively located to you in terms of your ability. So they start everybody with the middle item. If you do well on that item, they give you a harder item. If you do poorly, they give you an easier item. And let me tell you, there's no more fun in the GRE verbal test than realizing you are tanking it, because you start getting items like black is to white as, it's like, okay, this is not going well. That's my next item. But there's a happy ending because even though I tanked my GRE verbal, I still got into grad school, I still made it out, and I have a job. So yeah, boo to the GRE. In one of my other classes, the structural equation modeling class, I actually used the GRE as an example to illustrate standard errors of measurement, which is the exact same concept as standard error of the mean. And when you got your GRE score, they did not give you a standard error, did they? They don't give them out. So we have no idea how precise any one score is. And actually that data is available online, and it's a lot less precise than what you would think for a test that is so heavily used and heavily weighted. But the point of this course then is just using this as an example of what a standardized score is. On the current version of the GRE, the mean is supposed to be like 150 with the standard deviation of 10. Back when I took it, the mean was 500. It was on a different metric. But you know what the score means relative to some sort of standard deviation, standardized measure. In the examples we did last time with the twin study, comparing the population of the sample of twins to a population of typically developing kids, all of those measures had a standardized interpretation relative to a mean of 100. So in these cases, this sort of changing the metric of a quantitative variable to make it more interpretable or to convey its interpretation more quickly is known as a linear transformation. And the key idea of a linear transformation is that it changes all of the values equally. It does not change the distances between people in a way that is meaningful. So everybody sort of shifts along to the same extent. And this happens in statistics a lot of the time to try and remove differences between the scales of quantitative variables so that we can just think in terms of more absolutes in terms of how related things are. So as an example of this linear transformation, one of the things that we will end up doing before we put predictor variables into models for predicting outcomes is to do a process known as centering. This refers to either adding or subtracting a constant so that 0 is within the scale of the new variable. So if you pick the sample mean as the centering constant, this is known as mean centering or grand mean centering, depending on the author. So for instance, if I had a variable that was years of education, such as in the general social survey data set we're playing with, in this data set, years of education has a mean of 13.81. So in this case, what 0 means is that somebody who never ever went to school. If I wanted to make 0 a more interpretable value, I could subtract 12. I could center education at a constant of 12. And then the new mean would be 1.81. But what 0 means is that it would refer to somebody with a high school degree. So then 0 would be a more meaningful quantity, which is necessary when this variable is included as a predictor in a model. But all I've done is just take the mean of education and just shift it over. I haven't changed anything about the relative ordering of people or the distances between them. So you can see the distribution looks exactly the same. The only thing that has changed here is the x-axis. Another type of linear transformation that you will see a lot in statistics is the idea of a z-score. So those of you who've seen, had stat stuff before, does that sound familiar? Z-scoring. Isn't it funny how everyone agrees on the same letter? Right? There's 26 to choose from. You'd think that someone would call it Y scoring or U scoring, but no, it is Z scoring forever and ever. Z scoring is the idea of taking a quantitative variable and changing its metric, its scale, so that the mean is 0 and its standard deviation is 1. And to do that, you would take the original variable, so y sub I is y for each person, subtract a constant, so y bar is the sample mean, which is the same for everybody from that sample, and then divide by the sample standard deviation. And so that results in a new variable that we call z for each person here, and z has a mean of 0 and a standard deviation of 1. So if you want to talk about the association between two variables that are on different metrics, you can put them into these z metrics for convenience, and then the association is going to be easier to understand. That is the basis of Pearson's correlation, which we're going to talk about today. And to go backwards, by the way, here is a formula to un-z something to put it back into its original scale. One point of common confusion, though, about what z-scoring does, z is also the same letter that is used to represent the standard normal distribution. So do you remember that thing from before, like the bell-shaped curve where you would say 68% of the cases are within plus or minus 1 standard deviation, and then 95% of the cases are within 2 and 99 within 3? That uses the letter z as well. But this linear transformation does not make something normal. It only makes it have a mean of 0 and a standard deviation of 1. So it is not a normality-inducing transformation. So this variable right here, which we've been looking at in lecture 1, this is annual income in thousands of dollars for each person in the survey. It has a mean of 17, so $17,000. If I z-score it, the mean is 0 and the standard deviation of 1. But that thing ain't normal, right? It still has some kind of funky non-normal distribution. You can't really tell how these two things overlap because of the way that I've scaled the x-axes. But the point I wanted to make is that the resulting distribution did not somehow magically look like the standard normal. It just has a mean of 0 and a standard deviation of 1, which the standard normal also has, but this is clearly not that kind of distribution. So z-scoring is a way to strip off the units of a variable, put it into a scale where we immediately know what's what. So if I have a 5-year-old, like I do, and someday he goes up to school and he starts taking tests that matter. In kindergarten, they don't do that so much. He just builds maps. He spends all of his time building maps of the world. But someday he's going to go to school and take a test. And he's going to come home and say, Mommy, I got a 13. Yay? Maybe based on the context of the excited child, I would think that 13 is good. But I'd have to ask some follow-up questions to know how excited I should be about his 13. I could ask, well, what was the highest you could have gotten? Or how many points did Roman get, his current best friend in kindergarten? Because, like, like some sort of peer reference thing. But if he came home, and of course he's, my son, so this is going to happen, and he said, Mommy, I got a z-score of 2.5. High five, buddy. He's the child of two statisticians. He has no choice, right? This is just what's going to happen. He's going to come home and be like, Mommy, I got a z-score of 2.5. So what that would mean to me immediately, without any follow-up questions, is that he was 2.5 standard deviations above the average. That means that he would have done better than, doing the math in my head, 97% of anyone else taking the test, give or take. That's what about right what 2.5 standard deviations is. So Z gives you a metric that you immediately know what's up. If he had come home and said, Mommy, I got a Z of -1, I'd be like, okay, you were 1 standard deviation below average. You got to work on that some more, buddy. Got to put down the video games and hit the books. So z-scores help with parenting. I think that's where I'm going with this. So, all right. Questions so far? No? We're okay so far? Thumbs up if we're okay? And still awake? Double thumbs up. Okay, we're really okay. Excellent. So linear transformations is what we're talking about so far. Changing the scale of a variable so that you more easily know what it means. Nonlinear transformations are the other kind. And this is a transformation both of scale and contents. So in nonlinear transformations, not everybody's values are transformed evenly or equally. They are deliberately transformed differently to solve some sort of problem. There are two instances in which you will see this in statistics. One of them is when you're dealing with a variable that has boundaries and you need to make it unbounded. So this happens in models where you're predicting something like percent correct. A model of a variable predicting percent correct needs to understand that the highest value the model can predict is 100% and the lowest is 0. So the model has to obey those boundaries. It turns out that the way to make that happen is to transform percent correct into another metric that is unbounded and then back translate the predictions. We will see an example of this in computing confidence intervals for correlations. Because as we will see momentarily, a Pearson correlation is bounded. And so any confidence interval needs to understand that it has to stay within the boundaries. And the way to make sure that that happens is actually a nonlinear transformation of the R correlation coefficient itself. So we'll see that in just a little bit. The other is when you have skewed data and you don't want the people in the tail to mess things up. So for instance, if you have say annual income in thousands. This is a variable that has positive skewness. There's a lot of variables in social sciences that look like this, that are lower bounded at 0. One way that you can reduce the impact of the people in the tails is to do a natural log transformation. And to me, natural log is a function in Excel or a button on my calculator. Like, it had been years since I actually thought about what this means, and so I honestly had to look it up in Wikipedia to make sure that I got it right. So the logarithm is the exponent to which the base must be raised to produce this number x. What I think of the log transformation as doing is taking the positively skewed values and shoving them back over, and taking the negative ones that are piled up and stretching them out. So if I take annual income and I take the natural log of it, I do a log transformation, it looks like this instead. So where the lower values that were crowded around 0 here have all been stretched out into the negative space, and the positive values that were farther away from the rest of the data have been sort of shoved in. So you will see this as a way to make variables look more normal so that they can be included in analyses. This is typically not necessary. There are better models and better ways of handling that. But one way that this does get used in modeling in statistics is to create a different kind of relationship between variables than just linear. So that's something that we'll get a chance to see later in the semester as well. But big picture for right now, linear transformations just change the scale so that the numbers are more useful to you. Nonlinear transformations change the scale and mess them up to some extent. So they squish people or they stretch people differentially along the scale of the variable. So they do two different types of things. Okay. So reviewing in terms of stats inference about univariate variables, getting ready for bivariate. So the first instance in which we talked about the idea of inference was for a sample mean. So if you have a sample mean, which we're denoting here y bar, and you want to compare it to some sort of known population mean in situations in which that is available to you. In order to do so, you need the standard error of the mean, and that comes from standard deviation of your sample population, if you have it, divided by the sample size, so the n here, square root of n. And you can form a confidence interval, and you can do a significance test. And we end up with some sort of comparison of what we got onto this standardized space given by the t distribution, where t gets flatter and flatter the fewer people that you have. And so this is how we determine how expected a given result is for our sample mean relative to a population mean. We're going to use t to do the same thing. How expected is a bivariate association between two variables relative to what we would expect in a population. So t is coming back for more today. So bivariate, two variables. Before we can talk about how more than two variables relate to each other, we can start with just two. And which strategy you would use for examining a bivariate relationship is going to depend on what kind of variable they are. So you have to know ahead of time whether the variables that you want to see if they're related are binary, nominal, ordinal, or quantitative. Those are the four main categories that are going to dictate what logically goes next. And in each of these, I'm going to call them strategies or techniques for assessing bivariate relationship, we're going to get some kind of index of the strength of that relationship. That is going to be a point estimate. Point meaning the idea that it's just one number that's supposed to summarize that whole relationship. And we're going to be able to test the significance of that number against a null hypothesis, usually 0. So the same idea of if you're unexpected out in the tails, that is a reject the null hypothesis. It is unexpected. It is significant. If you're inside, then it's expected. retain the null hypothesis or do not reject, and non-significant. That same exact language and rationale we're going to use to describe bivariate associations as well. And so more formally, this is the process of what's known as null hypothesis significance testing. And I want to demonstrate this using our first measure of association, Pearson's correlation. So have you all met Pearson's correlation before? Anybody? A few people, not everybody, that's fine. So Pearson was a big damn deal. He is dead, but he invented like all kinds of stuff. So you're going to see Pearson's whatever attached to a whole bunch of different things. The good news is that even though there are nice, handy, easy formulas for Pearson's correlation, we can do them in software. So in order to get a Pearson's correlation between two variables, we will use proc_core in SAS or pw_core in Stata, where the PW stands for pairwise, meaning between pairs of variables, bivariate association. So picture time. So let's start by thinking about two quantitative variables. I'm going to label them X and Y. So numbers are numbers. To depict the relationship between them, one way to do that graphically is what's known as a scatter plot. These sorts of pictures right here, where one dimension, let's call it the X variable, would be shown on the bottom axis, and the other dimension would be shown on the Y axis, the vertical axis, and each of these points is one person's X paired with their Y. So it locates them into this two-dimensional space. The correspondence that that scatter plot shows can be captured by a statistic known in general as a correlation. So the idea of correlation has kind of a layperson definition. Like my mom might use the word correlation even though she's never had any of this. But there are very specific and multiple kinds of correlations. They're all designed to index some kind of relationship bivariately between a pair of variables. The one that we're talking about here in particular is called Pearson's correlation. And it has its own set of notation. In the population, it's supposed to be this P looking thing here. This is another Greek letter. This is known as rho, and the sample version is just R. Why it is R and not C for correlation, I do not know. But again, the whole world has agreed that it is R. It is not C. The nice thing about correlations is that, like z-scores, they are standardized. They're actually based on z-scores, so that's not a coincidence. But they range from -1 to 1 continuously. And the sign, -1 versus 1, indicates the direction of the relationship. And the size of the number in absolute value indicates the strength of the relationship. So going from left to right here, this first picture on the bottom left, it depicts a correlation that is +1, because as X increases, Y also increases, and it's lockstep. So there is a perfect relationship between these two variables. If I know your X, I can predict your Y with 100% precision. These pictures here show positive correlations, but this one is only strong and this one is weak. So there's somewhere between a +1 and a 0. So there's still the same pattern. People who are higher on X tend to be higher on Y also, but not a lockstep one-to-one correspondence. There's some wiggle in there. There's some imprecision or inconsistency in that relationship. If we get over to this, R of 0, that should just look like a sphere, like a circle of dots, where if you're higher on X, I have no idea what you're going to get on Y. So a correlation of 0 describes two variables with no relationship whatsoever. So the smallest relationship in terms of size is actually a correlation of 0. If we move further to the right here, now we're getting stronger relationships, but they're in the opposite direction. So these negative correlations then describe a pattern in which as X increases, Y decreases. As one goes up, the other goes down. So in terms of strength, both of these ending pictures here are of equal strength. A correlation of -1 is just as big as a correlation of 1. The only thing that differs is the way the relationship goes. A positive correlation means as one variable goes up, the other goes up. A negative correlation means as one variable goes up, the other goes down. They're both equally valid. And you can have either or in any situation depending on whether being up is good or bad, right? So if you think about things like exercise preventing disease, right? Hypothetically, since someone's exercising during class as usual, right? Like as exercise goes up, disease goes down, right? Because disease is bad for you. But if the research question were phrased as, does exercise improve health? Then you would expect that as exercise goes up, health goes up. So the direction can be whatever makes sense based on how the variables are measured. What we pay attention to is the size. 0 is the smallest, 1 or -1 is as big as it can go. And this type of relationship in particular is linear. So the fact that the perfect relationships form these lines is not a coincidence, because that is what Pearson's correlation is capturing, is a linear relationship as opposed to any other kind that you can have. And we'll see pictures of what else you can have. Okay, questions so far? Okay. No comments. I'm watching the chat window, I swear. And no worries about the internet. I know it doesn't always cooperate. I'm just happy y'all are here. Okay, so I'm going to show you the formulas by which you can do this stuff so that you've seen them and maybe have a conceptual understanding of how this works. But again, I'm not expecting you to memorize this or do this anything by hand. That's not how this works. So steps in computing a correlation, Pearson's correlation between two quantitative variables. First thing we would need are the means of each and the variances of each. And so this notation you have seen before, but I'm making it a bit more specific because now we're talking about two separate variables. So x sub I, this little x right here, that's one column in a data set that varies over people, so that is a variable. And to get the mean of x, which is given by x bar here, that's a constant, so it doesn't have an I. We sum up everybody's x's, divide by the sample size, that gets our mean of x. Same exact idea for y, except changing the notation to refer to a different column. Then we have the variances, and I am using a subscript to keep track of which is which. So we have the same exact formula for how to get a variance. It is each individual variable minus the sample mean squared so that the positive and negative deviations don't cancel out. Sum it up over everybody and divide by n minus 1. Do you remember why it's minus 1 and not n in this case?
Because it's a sample.
It is a sample rather than a population, but there's a more, I think, direct reason than that. What do we have to know to be able to compute a variance?
Is it because we are using the sample mean instead of the population mean?
Yeah, we have to first get the sample mean. And so the minus 1 refers to, like, how many things did you have to know to compute this result? More generally, you can think of this as denominator degrees of freedom. The idea that in any sample of n people for sample size, there's n things that you could know. And so every time you compute something, you take away a point. So we've computed a mean in order to get a variance, we take away a point. If we were computing this variance after knowing two things, such as an intercept and a slope, of a prediction model, then it would be n minus 2. If it was an intercept and 2 slopes for 2 different predictors, it would be n minus 3. So this idea of how many points did we have to spend to get to the point where we have this variance left over, that's the idea of denominator degrees of freedom. And so this is the first instance in which we see that. So once we have the means for each variable and we have the variances for each variable, the next step in the chain is this thing right here, which is known as covariance. So covariance, synonyms for this include common variance, or even collinearity is a term that people use when they mean the word covariance. Covariance is a way of saying how well two variables go together, but in their original metrics. So in this formula, it's just how far off from the mean you are on x multiplied by how far off you are from the mean on y. Sum that up over people and divide by n minus 1. So if people who are above the mean on x, so that would be a positive deviation for the first part, are also likely to be above the mean on y, then you'd have a positive covariance. If people who are above the mean on x tend to be below the mean on y, you'd have a negative covariance. So the sign is directly informative, even if the value for it is less so. So the problem with covariance is exactly the same problem that we were talking about with respect to a univariate scale for a quantitative variable. So if I have, say, a sample of 10 men, made up some fake data, and I have their height in inches and their weight in pounds. So here's my means for the sample, standard deviation, variance, the range. In my sample of 10 people, I asked SAS to compute the covariance between those two variables, and it worked out to be 135. So my index of how well age and height go together is 135 inch-pounds. And if you're thinking to yourself, okay, what the hell is that? That is correct. I don't know what to do with 135 inch-pounds. I wouldn't know what to do with 135 centimeter kilograms. There we go, metric. Either, right? So yeah, what do I do with that? The fact that the covariance is positive tells me that taller people tend to be heavier, but I have no idea to what extent that is true. So we're going to take this idea of covariance for association and standardize it. We're going to rescale it, so rather than having inch-pounds, it's in standardized Z units. So to do so, we take the covariance that we just found up here and divide by the standard deviation of the x variable and the standard deviation of the y variable. So that strips off the inch-pounds, and it leaves it with an x variable that has a mean of 0 and a standard deviation of 1, covarying with a y variable that has a mean of 0 and a standard deviation of 1. So the correlation, said differently, is the relationship between z-scored versions of these variables. That way we know right off the bat what it means. So in this case, you do the math. The correlation between height and weight in these 10 people is 0.99. So now not only do I know that heavier people tend to be taller, but that it is almost a perfect relationship between those two variables, which indeed that's the way I simulated the data. Okay. All right, let me go back for one slide here. Questions so far? So Pearson correlation is a way to indicate the strength of a relationship between two quantitative variables where the relationship that you're looking for is linear in form. That's going to be a key. So
I have a question.
Please do.
All right, so before we came to this one, we were talking about how to change this into an n-2. So is it going to be helpful for us to understand how to make this example into an n-2 as well, or?
I love that you asked that question because when I was first building these slides, I was like, why is it n minus 1? It should be n minus 2 because I had to get two means to do this, right? Like that whole thing I just said. So thank you for pointing that out. For whatever reason, let me fast forward here a couple slides. When we get to the hypothesis test for that correlation, that covariance, it is n minus 2. It is. But the entire world, every source that I looked at prior to that point has the covariance formula at n minus 1. It makes zero sense. So good catch on that. I think it should be n minus 2, and so does the correlation people. But for whatever reason, covariance is n minus 1. With enough people, it shouldn't matter because most of the time you're not doing data analyses on 10 people. But 10 people are useful for, descriptive things. Okay. Other questions or comments? Alrighty then. So one thing to keep in mind is that this formula for Pearson's correlation doesn't have anything to do with sample size in it. The two are unrelated. But smarter people than me have pointed out that that probably isn't a good way of doing a correlation. Because if you think about what happens in small samples, like if I only have two people, any line is going to fit 2 points exactly. So if I have two people, it's automatically a perfect correlation. That seems like a problem. So to try and get around this sort of bias, some folks have come up with what they call an adjusted correlation, where they take the R that you would have gotten from this formula and they try to adjust it based on sample size. So if I feed our result into this formula, I get 0.993 instead of 994. So it'll make a bigger difference the stronger the correlation, the weaker the correlation is and the smaller the sample is. And I have a note here that no one has ever asked me for this in a publication. But just in case reviewer 3 asks you, I want you to have this. And I'll show you how to get it in the software. By the way, I looked it up. It's not reviewer 2 must die as the Facebook group. It's reviewer 2 must be stopped. That's what it is called. I knew it wasn't quite that violent. That's just sort of my way of remembering it. But yeah, it is reviewer 2 nowadays. It's very rare to get a paper reviewed by 3 people. And I can tell you, as an associate editor at a journal, I'm lucky to get 2 people to say yes to this. So a lot of times I am the third reviewer who arbitrates. Is that the right word I want? Is that correct? I told you I tanked my GRE verbal. You got to help me out here. Arbitrates. It's not arbitrary. That's a different word. Yeah, anyway. So how do we know if a correlation is worth talking about here? Just like we couldn't just talk about our sample mean without knowing how it would compare across samples, we got to have the same principle in terms of a correlation. So we can do a hypothesis test as to whether or not our correlation is different than some null hypothesis. And it doesn't have to be 0, but often it is. So just to recall, a null hypothesis is whatever your standard is for what is expected. In example 1, lecture 1, when we were talking about comparing our sample mean to a population mean, the null hypothesis was that the population mean was 10 because that was how I simulated the data. So that is what I expected, 10. In the context of an association between two variables, the null hypothesis for a correlation is typically 0, meaning you expect no association, and your job is to say whether or not what you found is consistent with no association or whether it is unexpectedly large. So positive meaning unexpectedly a positive association, negative meaning unexpectedly a negative association, but still an association, just in the opposite direction. So the alternative hypothesis then, if it's a two-tailed test, is that it is not the null. So something other than 0 in the correlation instance, something other than a population mean of 10 when we did it in lecture 1. So we're sticking with the two-tailed hypothesis test. So more generally, the process of trying to figure out how to do a hypothesis test for anything that you want to compute in statistics, be it a mean, a correlation, or something fancier, you got to ask yourself, okay, do I want two sides or one side? And two is almost always the correct answer. How often am I willing to be wrong? So where does unexpected start? And so the percent of the time that unexpected would be is your alpha level. The percent of the time where expected is your confidence level. So you can phrase it in terms of an alpha of 5% as to where unexpected is. That is a confidence level of 95% as to where the expected range is. So those two ideas are complementary, alpha and confidence level. And then which test statistic you use to place your results onto some kind of standardized way of looking at them is going to be one of four letters. If you are only testing one thing, so the technical term for this, by the way, is numerator degrees of freedom, which is something we haven't gotten to yet. So one thing works for now. If you're testing one thing, it's probably going to be a T. If you have a large enough sample size to where it doesn't really matter, then it simplifies to a Z. Likewise, if you're testing more than one thing, it's going to be an F, which corresponds to T squared if it's only one, or a chi-square. So in practice, you're going to see one of these four letters as your test statistic. That tells you where you are on the expected versus unexpected continuum. That is the job of a test statistic, to tell you that. And so then if the p-value that you get, the probability that corresponds to that test statistic, is less than your chosen alpha. So if you find a result would happen less than 5% of the time, then that's reject the null, unexpected, is statistically significant. It is unlikely to have found what you got if the population null hypothesis was true. So everything is relative to the null as your baseline. Your job is to say where your result falls relative to that baseline. The other thing that could happen, if it's not unexpected, it's within expected territory. In that case, you do not reject or retain the null. Your result is non-significant. It is sufficiently expected, so within expected sampling fluctuation. And in practice, when you're writing up your results for a manuscript or something like that, no one ever says anything about the damn null hypothesis. That is not a thing. It is statistically significant or not significant or non-significant. So by the way, non-significant is usually written as one word, not significant is the two-word version. Got to be careful with the must-die stuff unless we accidentally set a mob on reviewer 2. Yes. Now there's not like a reviewer 2 hangout, as near as I can tell, where we could go, but I am absolutely not advocating violence. No. The best revenge on reviewer 2 is to answer all of their criticisms and get your paper published. That is how you beat reviewer 2. And by the way, have you guys had a chance to do that yet? To respond to reviewer comments on a manuscript? Jen, you have? What was that like for you?
I gave up.
You just gave up, pulled it, quit?
I sent in a second draft, and then they were like, "We want you to change this back to what it was before." I was like, "Okay, this is, yeah, I'm not doing that."
That would be frustrating. Yeah, all reviewers get a bad rap, but the thing to remember is that whatever they say, your first response is that you were wrong and that you're sorry. So I am sorry I was unclear about this. I am sorry I forgot to mention this. It's all about being appropriately deferential. And then you can say, as I've stated more clearly on page 13, ... And by the way, even if it was already there on page 13, your answer is the same. You are sorry and you have made it more clear, because odds are not good that they're going to go back and compare the exact wording to make sure that you actually changed it. So, yeah, good times. So yeah, my point though, the null hypothesis thing, that's sort of like it's the traditional language to sort of walk you into this, but that's not how people talk about it. So don't worry about that part of it. The idea is relative to the null as your baseline for what is expected. Are you too far away from that, or are you within expected sampling fluctuation? And within fluctuation depends on how many people you have. If you have a lot of people, expected fluctuation is huge relative to if you have very few people, in which case it's a much tighter window around what expected could be. There is a paper I put on your reading list, I think, for this unit. It's a classic paper called The Earth is Round, P less than 0.05 by Jacob Cohen. And so he's sort of, his arguments are against this idea of null hypothesis testing as sort of a silly thing to do, because when would you get something that's ever exactly zero? And if you get enough people, then everything is unexpected because your window of expected fluctuation is so tiny. So at some point it becomes less useful, and instead he wants to focus on effect sizes. There we go. Okay, which I agree with. So that's why I'm going to make sure that you all know how to do effect sizes as well as significance tests, because both are important to your story. All right, so significance tests then for correlation. If you have a null hypothesis, so notation here, HO meaning null hypothesis, that your population correlation, that's this P looking thing here, which is the Greek letter rho, is 0. So what I expect is that this sample came from a population where these two variables are unrelated. Okay, that's my baseline. Relative to that, what did I get? So we don't have a standard error as part of this process. So the standard error that we got first thing in looking at how the sample mean compared to a population mean, we don't have that here. Instead, we leapfrog over standard error and go straight to the test statistic T in this case. So it's T because we're testing one correlation, paying attention to how many people we have in our sample to test it with, paying attention to denominator degrees of freedom. And so the formula then is the Pearson correlation, and then sample size, and the correlation again here. So the only thing you need to know besides your correlation is how big your sample is. Your test statistic for where you fall on the expected continuum is a function of how strong the association is and how many people you have to detect it with. That's it. And denominator degrees of freedom for this T is n minus 2, as you would expect. So we can do a two-tailed test, typical alpha of where unexpected starts of 5%. The T for our example is 25. Even if we use the adjusted R, it's still 24. The p-value is 0 to a bunch of digits. And by the way, if you see this notation on your output, this is scientific notation, meaning you had to get 9 numbers before the actual values start. That means it's really, really small. So e to the negative means like 9 zeros before that starts. So we would conclude that it's super highly, very unlikely to have gotten a correlation of 0.99 from 10 people if the true population correlation were 0. So significantly positive, reject the null in this case. So do you remember where T, roughly speaking, corresponds to significant? I think we talked about this. It's somewhere around 2-ish. So that's something you can keep into your head. For a Z, it's 1.96 is the cutoff for where 95% and 5% separate. For T, it's 2-ish, depending on your sample size. So in practice for correlations, the software doesn't even give you T. It only gives you your R and your P and your sample size that it used for the R. So you'll go straight from R to P in terms of how you would report this information. Right. So if I had another example here, so 10 people, this time I made up 2 variables sampled from a population of 0, where the correlation is 0, I should say. And in this case, I ended up with an R of 0.25. The adjusted version of that R would be 0.24. And so it's negative, meaning as X goes up, Y goes down, but not that much. So a correlation of 0.2 is a small effect relative to a possible correlation ranging from 0 to 1. And in this case, if we plug that into our T formula, we end up with a T of minus 0.7. So we would see a correlation as large or larger as 0.25 if the true correlation were 0, like 49% of the time. So the p-value is telling us we are well within expected sampling fluctuation because a correlation of 10 people with 10 people is super noisy. It could be like anything. So expected is pretty darn far. Same conclusion, slightly different numbers if we used adjusted correlation instead. And I note that when you're reporting these numbers, p-values, you don't have to use leading zeros. In correlations, you don't have to use leading zeros either, because those are numbers that can't go past 1. Whereas any number that can go past 1, like a t-value, you should use a leading zero for that. So that's just something that paying attention to little details like that can make people happier to read your paper. Saying that as an editor and somebody who's super picky about those sorts of things. All right, how are we doing? So big picture, Pearson correlation used to describe how two quantitative variables relate to each other linearly, where the lowest it can be is a 0, highest it can be is a 1 or a -1. We use t to locate that Pearson correlation for our sample relative to the one that's given by our null hypothesis, and then we get our p-value that tells you the probability of finding a correlation as big as we found if the true correlation were the null that you expected. So everything is related to the null, which is why you have to know what it is in this case. And you could specify it too, by the way. So in this case, we have covariance that we get to correlation that goes straight to t, and this t then is a function of both r and sample size. So this is what Jacob Cohen is worried about, the idea that if I have a p-value that is significant, it could be because I have a very large correlation or because I have a very large sample. So just knowing that a result is significantly unexpected doesn't really tell you anything about how large the relationship is in an absolute sense. So correlation Pearson style here is actually unique in that it directly gives you an index of what's known as effect size, the idea of a magnitude of relationship on a metric that is readily interpretable. So I don't need to know anything else besides the correlation, and I know how strong the relationship is. Whether or not that relationship is strong enough to be called significant is a function of my sample size. More people makes it easier to cross that threshold. So if I have 100 people, a correlation of 0.3 might be non-significant, but if I have 500 people, that same correlation will be significant. So in practice, we want to pay attention to both the absolute strength of the association that's given by the correlation and the p-value for whether or not it's significant. That's a function of sample size as well. Alrighty. Do I want to go into this? Yeah, we can do this. I always have to look at the clock and remember, like, when am I out of time? When I first started teaching in this time block, like, I went over and people would be like, yeah, it's 1:55, class ended 10 minutes ago, why are you still talking? So it's 1:35, I'm good right now. Okay, questions or comments so far? We're okay? Hanging in there? So confidence intervals, in addition to conveying what the correlation is that we got, and conveying whether or not it is unexpected based on our sample size, we still want to try and convey the expected inconsistency of that correlation across samples of the same size. So I am talking about getting some kind of standard error. So we can compute a confidence interval that describes the range, but in order to do that, we need a standard error. And in this case, it's a little bit trickier to get a standard error and then to get the confidence intervals because correlation is bounded. It cannot go past 1. So to illustrate what I mean here, I've made some pictures. So I'm playing God again, doing a simulation where I have what's known as a bivariate normal distribution. So if a normal distribution looks like kind of like a mountain, a bivariate distribution would look like a taco. Like if you add the third dimension to sort of make it, a mountain that's in 2-dimensional space. I think taco is a good visual for that. So I simulated data from a taco distribution of 100,000 fake people and either a correlation of 0 as truth or a correlation of 0.8. So I know what the right answer is. And then I did the same random sampling process that I showed you for the sample mean. I grabbed 1,000 replications out of my population of 10 people, 50 people, 90 people, and here's what the distribution looked like for what the correlation is that I got back. So these are not people. These are correlations from each of my samples. I have 1,000 samples of 10 people, 1,000 samples of 50 people, and they all came from the same known population, so I know what the right answer should have been. So if the correlation were really 0, this is the expected spread of what the correlation ended up being in any one of those samples. And even though 0 is in the middle, like it sort of got it right on average, what I actually got spans almost the entire range of the correlation. So almost the full way from -1 to 1, even though the true correlation is 0. So when you have 10 people, you have no idea what the correlation is supposed to be. Another way of thinking about that is to look at the standard deviation for that condition, which is the first row in this table. So the average correlation from repeated samples of 10 people drawn from a population where the correlation is 0 is right on average. But any one sample's correlation is off on average from the population correlation by 0.34. So this standard deviation describing the variability of this distribution here is kind of like a standard error. That's the same idea. Any one sample's correlation is going to be off by 0.34 on average. So that's pretty big. The more people that you get, the less off it is on average. And so this distribution of what the sample correlations end up being is tighter the more people you have. So this feeds into the idea of what expected is, right? Like expected is the range here. It's very wide when you have very few people. If I look at a correlation of 0.8, now the distribution is skewed. Which way is this skewed, by the way, folks? More vocabulary. Is this positively or negatively skewed? Yeah, negatively in this case. Good. It's which way the tail went. That's how. And that's because a correlation can't go over 1. So where the other like half of this would be is all shoved in to the side here because it can't go past it. And that's all well and good if you don't have that many people, but it gets even tighter and tighter against the boundary here when you have enough people. And so if I look at, say, 10 people per sample here, the average correlation when I had 10 people in my sample, the true correlation is 0.8, the average one is 0.77, so not that far off on average. But any one sample is expected to be off by 0.15 on average. So if I use this 0.15 as a standard error, And a typical confidence interval is going to be roughly 2 standard errors on either side of this. If I use this R of 0.77 in this formula, and I put 0.15 in here, what's going to happen to my confidence interval? It's going to be 0.47 on the low end. If I have 2 standard errors around this, what's it going to be on the high end? .77 plus 2-ish times 0.15. What's the upper boundary of my confidence interval going to be? No one wants to be wrong. 1.07. Can I have a correlation of 1.07? No. So yeah, the idea that I can just do this like normal, get my standard error, get my confidence interval, it's not going to work. It's not going to work to the extent that the correlation is already close to a boundary, because the confidence interval needs to understand that it can't go past 1. So to solve this problem, I'll leave you with a cliffhanger for the weekend here. How we're going to solve this problem is a secret nonlinear transformation that goes by the letter Z also. So this is our 3rd kind of Z this semester. I don't know why, but this is not Pearson's fault. This is Fisher's fault, another statistician that has multiple things named after him, including F, which is Fisher's F. So we will solve this problem next time, and I'll show you in software how to not only get correlations, but their confidence intervals using this funky nonlinear transformation. So stay tuned. All right, any questions before we call it a day? All right, then please do formative assessment number 1 before Tuesday. You can start homework 1 if you feel like it, and otherwise let me know if you need anything, okay? All right, stay safe, stay warm. See you next time.